Haidinger's brush, birefringence theory, ex vivo optical recreation, and modeling of this entopic phenomenon, presented by Sean McCafferty, Joanna Rosenbluth, and Meredith Kopinski. Affiliations with the University of Arizona College of Optical Science and College of Medicine. We have no relevant disclosures. Haidinger's brush is a phenomenon in the human eye in which we can see the effects of linearly polarized light. Since the time of its discovery, it has been described solely as an entopic phenomenon, unable to be optically recreated outside of an individual's visual perception. It is observed as a faint crossed yellow and blue bow ties when observing linearly polarized light, and which you can train yourself to see, but it's difficult to unsee thereafter. First discovered by Wilhelm von Haidinger, also known as the Wolverine, who was a mineralogist. It was observed examining minerals under polarized light. This is the same Haidinger of Haidinger's fringes, which we commonly use today, as shown here in an optical flat. There are clinical applications of Haidinger's brush, first in training macular fixation. Also, macular birefringence is used to quantify binocular fixation errors for treatment and potential surgical correction. Two theories have been proposed but without demonstration of the brush phenomena. The first states retinal pigment xanthophylls preferentially absorb linearly polarized light in a given orientation, specified by the polar orientation of the macula. The second theory is due to macular birefringence, which has been demonstrated in the radially oriented retinal layer called Henle fibers. Both theories are not necessarily mutually exclusive, but Haidinger's brush will show is easily demonstrated with retardants. The oldest theory, that of macular pigments filtering out blue light, is supported by blue absorption by retinal pigment, as theorized this improves contrast and protects the macula from harmful UV exposure, possibly associated with macular degeneration. The pigment absorption theory is supported in studies examining polarized light sensitivity in specific animals where the radial orientation preferentially attenuates polarized low wavelength light with a specific linear orientation. With this, it has been calculated that pigment molecules, even as much as plus or minus 55 degrees from the normal to the radial projecting Henle fibers, are enough to create the attenuation needed to produce Haidinger's brush. Utilizing the birefringent theory, initial observations were able to optically recreate the orthogonal dichroic effect using a linearly polarizing filter and a 45-degree fast axis oriented quarter wave retardance plate, as shown here, 90 degrees from each other. Building upon this observation, shown here is a radial orientation of the linear polarization with the appropriately oriented quarter wave plate to produce Haidinger's brush in a discrete fashion at 90 and 180 degrees. This is easily extended to progressively more radially continuous demonstration as the number of radial subdivisions increases. Our observations enabled demonstration of Haidinger's brush optically and not as an entopic phenomenon by observing linearly polarized light through the radially oriented linearly polarizing filter and the 45-degree fast axis oriented quarter wave retardance plate. This optically recreates both the accurate dichroism and the orientation which are specific to Haidinger's brush. Furthermore, Haidinger's brush can be modeled in a Mueller matrix analyzing linear polarizing light through a radially oriented retardance element with varying retardance values as shown here. Using this Mueller matrix model, Haidinger's brush appears to be maximally reproduced at between a quarter and a third wave of radially oriented retardants. In summary, this is the first ex vivo recreation of Haidinger's brush and provides strong validation of the birefringence theory. The birefringence is likely a result of the optical property in Henle fibers, but the human cornea also has similar properties. This allows a deeper understanding of the eye's polarized optical physiology. Additionally, the radial dichroic filter potentiates the use of a color indicator able to determine the orientation and strength of linearly polarized light.